Hey, Bradley, how are you?
Hi, how are you?
Good.
So, how are you enjoying the article here? I saw you posted some things in the Slack.
Yeah, I posted what I took to be maybe like the main ideas most
Okay.
relevant to us.
Okay.
Um, I am still. I feel like I would need to really dig into a lot of these references to fully understand the paper.
Yeah.
Um, and I think the screenshots I shared show like the most important parts that are still very unclear.
Yeah.
um,
Hello.
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 So yeah, I was just saying I shared a couple of excerpts in the group in the Slack channel. And those are ones that I took to be like both the most important for our purposes and also still the most kind of unclear. Specifically, it's interesting to me because he is saying that our storage metaphor is imperfect. But it seems like at the end of the day, he still is talking about this in terms of storage, that memories are they're stored in this interesting way that involves compression in this bow tie shape. But ultimately, it is still storage. We have no direct access to our past at each present moment. To recollect the past, we have to reconstruct it dynamically from the engrams left in our brain and body by the activity of a past self. So those engrams are still, while it's not like a video recording of an episode of memory, it's something that is stored, and every component of the system, including but not limited to those that bubble up to conscious recollections, could be using everything in its environment as an interpretable scratchpad. The deep levels of biological structure and dynamics offer an incredibly high dimensional reservoir, referred to as the senome, that can be exploited for memory remapping. In this view, neuronal networks are not so much used for holding memory as they are for learning to interpret the engrams embodied by subcellular components. So I guess my concern is, okay, so memory isn't stored in the brain in the way that is often described, but okay, so it's stored in the subcellular components. I guess I still, my question is, how is this still like a problematic usage of the storage metaphor?
I don't know. Why don't we pull up the paper? This is the first quote that you mentioned. So this is the future work section. This is nature of the memory medium, how it facilitates reinterpretation, and the invariance of saliency. So he's talking about reinterpretation and invariance. Okay, so it means you don't want to have salient things forgotten, or you don't want them to be different across lifespan. So it improves your ability to recall things, and then it actually allows you to recall memories. It's a structure that facilitates not only just recalling not just a photographic memory, but like reinterpreting something in different ways. So then he says, if engrams are not in the synaptic structures, where are they? So this goes back to that discussion we were talking about with engrams, and where they tried to find the engram as like a single patch of the brain, but then that search failed. That was Lashley, and then later on, more recently, people have proposed that the engram is sort of this network, this distributed network. So we might argue, well, okay, engrams are in the synaptic structures, and then I guess citation 217, which we can follow up on here. We'll look into that in a minute. Where are they? So to understand this part, we'll have to go to 217. My current hypothesis, driven by the above multi-scale perspective, which is 218, look that up as well, is that there is no single substrate for memory. So what does that mean, no single substrate? It means it's maybe like a multitudinal thing where it just cobbles together whatever mechanisms are there to encode it. There's a footnote 49. We can look at that as well. Every component of the system, including but not limited to those that bubble up to conscious recollections, could be using everything in its environment as an interpretable scratch pad, which is footnote 50. So that's, I guess, interpretable means, I guess, something that we can understand, or that it can be understood by the brain itself doing things. I don't know, because they use this scratch pad metaphor a lot in cognitive psychology for like working memory, where you're storing things. If I give you a phone number to remember, you'll remember it for a short time if you repeat it. And that short-term memory will last for a while until you get more short-term information. And then, it either gets encoded into long-term memory or you forget about it. That's why, when you get a phone number, you have to write it down or put it in your phone. And then if you don't do that in a certain amount of time, you forget it. And then, so that's kind of what, that scratch pad metaphor is also very interesting with respect to memory.
I've heard the scratch pad metaphor used when talking about extended cognition. So like a literal, when you have to use a literal scratch pad.
Yeah.
So this is saying that it seems like the environment becomes a part of cognition in a substantial way.
Yeah, that's why we use scratch pads for things like we write down notes, we don't lose it. Because if we just put it all in this short-term memory buffer, it would disappear, most of it. We can't rely on it to go to long-term memory because it's not the way. There's a bottleneck there. So we write things down in books. So we have books. That's why we have books. Not everyone remembers every detail of a book. You read a book, you kind of get some sense of the words, some sense of the story or the details, but you don't memorize. Most people don't memorize every word of a book. And unless you're really devoted to a book and you memorize passages, but then again, those are kind of like it's a highly ritualized thing usually, and it's not necessary really. I mean, you can just consult a book. So yeah, that's okay. That's the scratch pad, and then the deep levels of biological structure are dynamics and dynamics offer an incredibly high-dimensional reservoir. This is 223. I don't know if he's going in the direction of reservoir computing here, but referred to as the senome, which is, I didn't know if it was C-nome or SE-nome. This is a senome. I don't know where they're, I guess that's 19 and 227.
I think it's supposed to be sensory genome, if I remember correctly.
Okay. Yeah. And that's another metaphor on top of that. That can be exploited for memory remapping. That's footnote 51. So this is like, kind of building on, first of all, a couple of metaphors. We have the scratch pad, we have this reservoir, we have the senome, which I assume uses some, if it's using a sensory type model, it's probably has connections to ecological psychology. So yeah, this is like, and then in this view, neural networks are not so much used for holding memory, so for learning to interpret the engrams. So that's like the engram was, of course, viewed as like this single unit in the brain. And then it's like, that's the unit of recall. And you get this, like, basically it's like a photographic thing. And then you recall it from that location and it gives you a photographic recall. And then I guess you put those together. Well, what he's saying here is that you're basically, you have an engram that needs to be interpreted. So you have maybe a place in the brain where it's stored, or a network where it's stored across, and then it has to be interpreted outward. So there's this other component that comes out. And then those are the subcellular components. So those are references 34, 35. That's that part. Then the other thing is here, these dynamic features of our mind soften our connection to the ground truth of what actually happened in our history. We cannot really trust our memories of the past in a much deeper way than just an inability to remember some details. We don't just perceive the past like we might perceive the present, like if we were to go out and walk around and engage in this naturalistic cognition, but rather modify and rebuild our mental model dynamically. So that sounds very Gibsonian, but it does stand in contrast with the sensory aspect, because the sensory aspect is sort of the direct experience, and the memory is, of course, not direct experience, although it could be shaped by direct experience. We have no direct access to our past. At each present moment, to recollect the past, we have to reconstruct it dynamically from the engrams left in our brain and body by the activity of a past self. So that's interesting, because we talked about the example of metamorphosis, and like if you have a caterpillar and it has these memory traces of what it needs to do as a caterpillar, and then it goes into a cocoon stage, it decellularizes parts of its body, gets rebuilds a new phenotype, and then it's basically got those memories but with a new body, and then ostensibly with a new set of experiences, a new kind of set of engrams maybe, but also it's interpreting things from those other memories. So it's almost like you have memories from some experience, but it needs to be reinterpreted. I don't, unless he goes into that more somewhere else, I don't know what the model would look like for that, but that's just an interesting thing to think about. Do you have any comments on that?
Well, so one important piece that isn't captured in these screenshots is that there's like there's like noise in the engram, like because he talks about the genome as well as seeming to involve all this extra stuff. Like it's noisy, but that's supposed to give flexibility. So the way that the information is compressed when the memory is stored and the engram is stored allows a flexible reinterpretation. And that is supposed to allow the butterfly to remember what the caterpillar encoded, despite the radically different physical makeup.
Yeah, it's interesting because in an engineering context, people would think of like noise in something like a memory controller or any kind of controller as being bad in a lot of ways. And,
right. Noise doesn't seem to be the right word. It seems to be like, it seems like noise once you reinterpret the engram in a particular context. Like the stuff that didn't end up mattering for the reinterpretation looks like extra, but it maybe wouldn't have been extra if the new context were different. So it's like what ends up being salient depends on the new context, and the way that the memory is encoded allows it to be useful no matter what the new context is my best understanding.
Yeah. Well, maybe we'll look that up a little bit too after this. Okay, so that's, and then continuing with this, one can think about our apparent continuous stream of cognition as a series of frames or selflets. So this is another term. And selflets are like slices in the breadloaf model of special relativity. So this is like, I guess, in special relativity, or the space-time model of a bread loaf model of space-time, and then you have slices of that space-time that are the selflets. I don't know. It's interesting. I know he likes to talk a lot about relativity, like physics models of space-time as like a way to map what is going on in this naturalistic cognition to some conceptual model. So that's kind of where this is going. Each being probably a few hundred milliseconds thick. So let me see. So it's like a space-time slice that's a few hundred milliseconds thick, based on our studies of cognition that are where we do experiments and we have a few hundred milliseconds of activity that we record. I don't know why he picked a few hundred milliseconds. I wonder if that's like the fundamental time unit of sort of an experience, or is it just kind of based on this sort of, what we kind of contain as a neural response to some stimulus?
Right. I was also wondering where that number came from. Is it something to do with something measured by like EEG, or something about subjective reporting? Because like we were talking about a little bit last time, it seems like that's a number that could vary wildly person to person, depending, or more likely, I guess, like creature to creature, based off of an animal's metabolism or something. How, like, just like, yeah, the speed of information processing. But in the context of memory, it's like the unit that how long it takes to encode the engram, maybe, which is distinct from just what you can perceive. Yeah, I don't know. I don't know where that number came from.
Yeah, well, let's see. I don't think he has a footnote there, so that's just going to have to be like his estimate. I think it might be something like where you're measuring kind of, you have like these experiments where you present a stimulus, it gets processed. Maybe it gets like there's a memory, like it goes from sensory information to some sort of maybe short-term memory. Well, we know that like long-term memory, at least the theory of conversion to short to long-term memory, suggests that we have these short-term memories that are like very, they can be stored in a buffer and maybe longer than a few hundred milliseconds. And then some of them get converted to long-term memory if you get exposed to them enough. So if you keep seeing a phone number, you the first time you see it, you have to like store it somewhere, maybe in a notepad or on a phone. You see it 4 or 5 times, then you kind of memorize it. You have your own phone number. Maybe I'm not very good at it, but you'll memorize your own phone number because you encounter it a lot. So that process is going to be longer than 100 milliseconds. He's talking about selflets, so it might be like self-reflection or self-experience. And then that either goes, that kind of vaporizes or gets encoded in the engram. But yeah, I don't know where that number comes from. We'll have to go to figure 1 actually to see. Well, that might just be a diagram of things. Yeah, but that would be kind of fall into the engram encoding process. How long does that take? And I suspect it's going to be at multiple timescales. Like, you would have like this short-term memory that gets converted to long-term memory, or something you can kind of recall more easily than not. And then maybe if it's something complex, not like a phone number, but like an image of like a famous work of art, you go there to see it once, and you see it and you remember details about it. But then if you go and revisit it maybe 5 or 10 years later, you're building upon that memory and you're kind of augmenting with the current experience, and I didn't notice that before. Yeah. It's just kind of, or, when you stare at one of those magic pictures, it takes a while to sort of get the focus your visual system on it, notice details. That's very longer than a few hundred milliseconds, but you spend time on it and you kind of notice new features and you remember things from it. So, okay, yeah. So, do you have any other comments?
not about these quotes, I don't think.
Okay. So this is all right. Then the final thing here is, from this perspective, memories are messages between agents separated across time. So memories, or at least the way Levin is defining this, at like memory. Of course, we can define it in different ways. They're messages between agents. So I guess this means like you might have two organisms sharing information, or you might see some information in a, I guess maybe he's not talking about that, maybe he's talking about within the brain. But anyways, agents separated across time. So there's this temporal aspect. And then it's each engram is stigmergic. And so now I will define what stigmergic is. And stigmergic note. So a stigmergy or a stigmergic is, if you're familiar with social insects, like ants, we'll use ants as an example. Ants will behave in the following way. There's a good example of like extended cognition. So ants are these agents that will sort of, they'll behave collectively. They're very highly social. They have different roles that they play in their community. And if you watch like ants, go out into the world, sometimes they'll go out in search of food, and you'll see them marching in a line, or you'll see them like kind of swarm around like a piece of food on the ground. And they do this. They have to sort of communicate with each other to coordinate their activity. And so they'll lay down this pheromone, which is like excreted by each ant. So like ants will go out in the environment, and they'll go out in these different directions to explore what's going on in the world, find food. They're laying down this trail of pheromone behind them, and then other ants can detect that pheromone. And then if there's an ant that finds food, they know, where the ant is that found food, and they can follow that pheromone down to the food. So eventually all the ants sort of reorient themselves down a single path that has, this pheromone, and the pheromone builds up as more ants come through, and it leaves this thick trail of pheromones. So now the ants know exactly where to go, and it organizes this collective behavior. So if you go and you look at a trail of ants and you wet your finger and you cut across the trail, the ants behind where you cut across will kind of bunch up behind where you cut the pheromone trail, and they'll kind of get disoriented. And then eventually maybe they'll find a little trace of the pheromone, and they'll kind of continue the trail, and they'll go through. I don't have a video of that, but that's basically what happens. And so that suggests that they have this thing that they're putting down in the environment that is acting as this sort of memory buffer, or this memory trace, because each time an ant explores their environment, they're laying down this pheromone. It's like basically a memory trace of, okay, this is where we need to go. This is where I've explored. And if I find food, then this is where we need to go. And they can share that with agents. So he's talking about stigmergy. He's talking about something like social insects or ants. And that, that stigmergic thing is like where they'll lay down some marker in the world. That thing then is the memory of what's going on, the exploration effort, whatever. And then there's this social cognition that goes along with that. And so it's interesting that, he talks about this within the body as opposed to within the environment. But basically, stigmergy is where you use these cues, these kind of memory traces to coordinate collective activity. And in the brain, I assume he means that, like, if you have a distributed engram, there's a similar process where the engrams interact and they kind of find the solution through their interactions. So that's interesting that he brings up stigmergy in this way.
Yeah, I was just want to comment about, I think ES extended and the phrasing also is a little bit curious to me. I went back and forth about how to interpret what he said about like between agents and um almost I don't think this is what he means, or is it what he means, but like almost like even the same agent across time, as in like an agent isn't necessarily the same agent across time. Like I don't really know what to do with that. And I'm not sure I don't really know if that's a valid question to get into what he's trying to do. Um Same agent across time, yeah. But almost like yeah, I don't know. I'm still sorting it out. My mind's a little bit my RAM is very taxed and I have other things in my mind. But I'm trying to like sort out. I have a lot of thoughts and feelings that are coming to me very slowly about this, so I'll kind of be in the back seat for a bit more.
Okay.
No, I agree that it's an odd way to talk about like one human being across time. But maybe going back to the butterfly example, it's a little easier to think of the caterpillar and the butterfly as different agents, or I guess even just like a young child and an adult.
Yeah, exactly.
Which, but nevertheless, the adult has access to the engrams that were formed by the very young child.
I would even say very specifically like human being. I think that was
Yeah.
2 moments there. I don't. I was saying it in the sense of it, even for me, like it's not. And I don't know what this means as for my, you know, conventions or norms or how far off the market. And it actually almost makes more sense to me to think to directly center, like yes, like it is the same agent in one light, and then not like you are not the same agent in another. And I'm not trying to be. I don't even mean from sort of a higher level woo woo spiritual. You never step in the same river twice, but more like almost legitimacy of at least in my like in a human sense, it may actually be more um I don't know a stronger comparison to a butterfly across its development because of the radical shifts that are happening in um, human social, psychosocial, biological developmental spaces. And what I was looking at all the four E's and the extended, embodied, and active, and it's like this touches upon all of them in different ways, and that's one particular lens and model. But I I think part of what stumped me is sort of sitting in the sense that like is it this sort of paradox of it's the same agent and it's not the same agent. Like it is an agent, but it's you know it depends a bit on the binning, the separation of what time are you looking at, and what's you know there's some contextual relations that aren't there. But to go back to Bradley's nice discussion about extended and the what was it, stigmergic, what was it called?
Yeah, stigmergic.
Yeah, and that like that's I know I've kind of said this last time a lot, but um it fits with this sort of ensemble, this orchestra, this coordination of various things across different domains. Not just in the tracking, but the sort of there's a something being uh put in there, and there's sort of a physical like, maybe a physical okay in a pheromonal smell olfactory putting something down in the ground or in the space and the ant sense, and there's like all the stuff that we have about you know writing and books, and even thinking about what was said before about you don't really read or remember the whole book necessarily, and to what degree, and even the comment very I think there's a lot in the comment of unless you're like doing it in a ritualistic sense, yeah, like unless you're putting an intentional practice or like emotional affective meaning, like it has to be meaningful to mean to know to that degree. Like why is the resolution so high? Why does it need to be so high to know every word, every sentence, every footnote about it? And I think those are all different, like it's almost like we're trying to get at these different properties that are not necessarily fixed. There's sort of a if you're coming at this through an approach of, well, I just want to need the cliff notes, the summary, the spark notes, that approach and that intention has a very particular filtering, you know. And does that mean the memory changes, or does that mean your relationship to the material, or the internal, the external? Like, how does it affect the different, uh, I don't know. I feel like it's such a cop out to use the word affordances here, but the means of relating to the memory, like to the information or whatever is it. I'm kind of blurring the lines here between talking about memories and like other things, but it's sort of like, yeah, it's interesting to kind of step out from the in depth thing here, like uh, memory, and the way I'm talking about memory most in the last 30 seconds is much more akin to memory as a sort of um, interfacing mechanism than a thing. Like it's not really the way I'm talking about it is it's more like a um it's not really like a GUI, but um a a, a f- something that connects front end and back end in some form, as opposed to a thing. And I don't really like I don't know that that's I don't really know what to make of that yet. I don't know if that's an opinion on more of a specific facet of memory or whatever, but that's what's coming out from this. So
Yeah. Well, yeah, we were talking about short and long term memory, or maybe a better way to put it, a sensory experience that you sort of have a short term recall of, and then long term encoding of that. So, if I look at a scene, I can like look around a scene, different points, and then I can remember to go back to a point to revisit it. If I'm looking at a painting again, I might look and visually inspect it. Oh, that's cool. And then, oh yeah, let me go back up to this spot and look at it and make a connection there. And that's all like kind of the short term buffer of, sensory driven kind of recall, and doing things in the moment or whatever. And then, there's the longer term memory, which is when I leave and I think about that painting over the next couple of days. I'm remembering details about it, not the whole thing. And maybe you do have, we talked about eidetic memory last time, and then if you have an eidetic memory, you might see the whole thing in your mind. But usually we don't worry about the whole thing. We just kind of like remember details, and then kind of ruminate on those. And so I think there's an interface in that sense, and it's like in the sort of the conventional theory of short to long term memory conversion, there's the interface. But also the interface between like sensory experience and then something else, um, where you have this reflection on what you saw. You don't have the sensory experience available to you right now, but you do remember things.
mhm.
Yeah.
Yeah, I will eventually call upon the thing about the painting that I put in the chat, but it the actual physical, I don't know, physical, but the engaging of the perception and the encoding seems almost, at least for me in the moment right now, like there's something very, very emotional and visceral about it that isn't, that's, I mean, I think we all know this here, but just kind of say this to the audience at large. I'm very obsessed with the concept of alternatives right now. I always talk about the Norbert Wiener quote, alternatives and information fusion, but I it, I'm really interested in the topic at large, and I should write a lot of more things about it. But in this context of the memory thing and the encoding, it's sort of like there's something about meaning and that part of it and the nature of alternatives, or at least that there's something to differentiate. Um, and I don't have a finished thought about that, but to tie it to the painting remark, I, I don't know. I don't think this is a surprise to any of us, or we might have been talking about this before, but I'm referencing something where there's a study in some famous museum, and they had people look at a poster of a classic versus the real thing. There's obviously different, activity, sure. And I think part of that difference is sure aesthetic, beauty and all, but also um, the real thing has a you know um, almost like, and then maybe this goes back to the noise question earlier somewhat too. In one sense, you could see the details of the physical painting as arbitrary noise. Like maybe it's a distortion in how some of it would be encoded in a sort of a pixelated sense. Like, oh, well, we have to just refine and smooth this, otherwise it's not going to be clear. But in another sense, maybe it's like what that is a sort of, I don't know, extended-ish residue of like a temporal data of something changing over time, of decisions that were made. Like there's a decision being made about how the brush stroke was laid out and carried out and changed or not changed. Yeah, that's something that's stripped away. It's sort of merged. Wasn't like in Photoshop, like merge and flatten. It's merged and flattened into the poster. And so I think those are all um, at hand. I'll leave it at that for the moment.
Yeah, I think when he talks about invariance, that's interesting because, like, if you think about like in information theory or in like feature selection in a machine learning algorithm, usually you're looking for invariance in an image. So you're doing like, you might like see things in the shape of a triangle, or you use a computer vision algorithm to find like triangular shapes. The triangular shapes can be anything, it doesn't really matter on what the pixels are. It's just that does it form a triangle? Can identify a triangle? And everything else. So from the algorithm's perspective, the triangle is what counts. Everything else is noise. So there are variations on the triangle. It could be maybe imperfectly shaped, or it could be like embedded in some other scene, but it's there. And then everything else is kind of like variations on that. So when you do like computer vision, you're like interested in the invariance, and then the rest of that is variation that is, although interesting, it's not, it's kind of like, it almost trains your algorithm to be like generalizable. And then that's maybe what kind of where that comes in, where it's sort of that view of noise where it's almost like variation, or like what we might call variety in the Evergood regulator theorem. All right. So I don't know, Amanda, did you have anything else you wanted to say? Or
Yeah, I was thinking about, so it's definitely right that your mental state and your attitude and what you're after in a particular moment will affect what you remember. Like if you're reading a book and there's some problem you're trying to solve, then you will likely be have stronger memories of the parts of the book that are maybe ended up being relevant to your problem solving or something. But my understanding of one of the main points of this paper is that somehow you encode, you remember more than what you like know to be relevant at the time, because somehow what you encode is potentially useful for a bunch of different versions of future you.
Yeah.
Now that's the part that's a little difficult to wrap my head around.
Yeah, but I get kind of where you're going with that. It's like you're taking not just the invariance, or the sort of the main idea, but some of the details maybe that allow you to generalize to other things. Like if I see if there's a character in a book, and then I read it, and I kind of get the sort of what they're doing. I need to not only remember that, but I need to remember how maybe it relates to some other character. And maybe not like purposefully, but like just kind of like that's how it happens to get encoded, and then I can make that relational step later. Yeah.
Yeah. I have something I could say there, but I don't want to distract with it. You want to say more, Amanda?
I don't think I have more to say. I shared another screenshot in the chat of a table of other examples of this kind of compression, if we want to look at that at some point.
Okay. I'll jump in and say, based on what we just said, I think one of the most interesting things about that really hits me, what Bradley and what you guys just said is basically the phenomena of me. This is maybe very specific. It's a general thing, but also I think something kind of unique to my generation as a millennial, because I listened to music of many different eras as I was growing up, or had access to it. But at the time, maybe like 10 years ago, the ability to search for music and songs and lyrics was definitely not as robust as it is now. Like you can really find a lot of stuff now. And where I'm going with this is I very strongly believe and very vividly remember certain songs going a certain way and having certain lyrics. And I enjoyed being right in that in my mind and how I felt about it. And there are times where those songs and those lyrics were not at all true. And I think this is, I'm really leading into sort of emotional, visceral stuff right now, but I feel like that's, that to me speaks a lot to what it is that the encoding memory part, like what to the point of like you're encoding more than just the memory, you're encoding more, or you are prioritizing something as a sort of a whole, and then there's a preferred like handling of it, like almost like how you have maybe a dominant hand of grasping, there's a preferred approach to it, like, oh yeah, this song in my mind is really great, I love it, I love that song, I love those lyrics, love to sing it this way. And it could be totally not, it's not about, I think what we're kind of getting at, and I'm my mind is not able to interface with the paper very well about this, so I can't really get to what Levin's saying. But memory is not about, facts per se. It's about a record of a certain kind of salience that has, and then I even think like there's not a sense of, oh, people are rational, but more like mm, the validity of why that's like the evolutionary need for that to be the case. Whether it's simply just the amount of data that has to be filtered or compressed into something salient or meaningful, but also like the phenomenon that I talked about with the song thing, like that's sort of a peacetime situation where I'm not under duress. I'm just remembering something in a way that's a little bit more appealing, a little bit of pretty thoughts, a little bit of rose-colored glass, a little bit of I enjoy it being this way, so I'm going to see it as that. It's not the same as being under duress or survival, or I better over anticipate the tiger in the field, that kind of stuff. And so um, it's sort of like memory as a um, memory as a narrative reinforcement, or memory as a thing, and like differentiating that clearly from memory is not doesn't have to be um, there's sort of a teasing out this nuance between memory as something that's happening, something that's encoding, something that's meaningful, and also like the objective, factual, empirical reality of whatever that situation is. And that's okay. Like that's not, they're all parts of it. So it's how do these parts, relate? And there's sort of the different sort of arenas that the stigmergic activity is playing out upon.
Okay, so last part of this, I want to go to this table that Amanda posted in the Slack. So this is from table 1 in the paper. This is where we have scenario scale. I guess this is kind of like thinking about different types of, contexts, diverse examples. Then we have this Bowtie hub node, which is something from network theory where you have like two modules of networks that are kind of connected by a single node. So it forms kind of like a bow tie. So you have like one set of nodes that are connected on the top, one on the bottom, and then it's connected by a single node. So it's like this bow tie. It has that shape. And there's a in like if you go into the bioinformatics literature or even into the network science literature, these bow tie hubs serve a really important purpose in information processing. That is, you have basically two networks that are highly dependent on a single connection or a single small set of connections. And it has this bow tie quality where it's like translating from one network to another, one network module to another. That's what I guess he means by bow tie hub. The hub being this single node that connects all these other things. And then there's this remapping process. So let's go to like hologram, which we talked about last time. Hologram is the example. Holographic film would be the Bowtie hub node, which would be like where you store a compressed complex 3D pattern, and that would be one network module. And then it goes to this Bowtie hub, and it goes down to this other network where it's a map from that complex 3D pattern to a 2D substrate. So if you ever looked at a hologram, it's on a surface, but if you look at the surface and you move it around, it can reflect the three-dimensional information in that pattern that the substrate is storing. So you have this three-dimensional information on a two-dimensional surface. Then remapping is done through laser interrogation. So that Bowtie hub, that translation process is done through this laser process where it's lasering on to the 2D substrate, this pattern. It talks about hyperembryo groups. That's like a calcium ATP signal through a medium between embryos. This is where you have multiple embryos in a single set in developmental setting. It could be an egg. It could be in some other place. And you have these ATP signals that communicate between cells, but also between embryos. I think this is specific to a paper that he published with some co-authors on multi-embryo settings in development. And so in the remapping process, it's increased morphogenetic problem-solving competencies. So this is where, you have these multiple embryos, and they use this calcium ATP signal to coordinate their activity, and they can then form, structures and do this in a way that's this sort of stigmergic aspect. So there's this collective cognition aspect to this. There's single cognitive self across time. The Bowtie hub node is memory media engrams, or memory media, which is made realized through engrams. And so it's like this memory substrate. And then the remapping process is the neural interpretation of engrams. So you have these engrams, which might be small network modules. It might be like in a small group of neurons, an assemblage of neurons. And then those things are connected to these Bowtie hubs, and then to maybe further information integration centers, where that's what he calls neural interpretation. Same thing between transplants between cognitive selves. He has these extracts of RNA, which is usually something you can get out of a cell, and it's just a bunch of free-floating RNA. Or you can have tissue implants, and the same thing is neural interpretation of engrams. I think a lot of these are from his own work, so it's kind of like, with Levin, you're like building upon his work. So he's like writes a paper, and it's really interesting, and then he'll use that example in a table in another paper. So it's kind of like he's building this massive library of Levin, the Levin bot work. And then, you have to like be plugged into that work to really know what these examples are and their implications. He talks about art, which is poetry, paintings, etc. And the remapping process is personal interpretation, finding personal meaning. So there are a bunch of, there's stress with the integrated stress response. There's a developmental lineage and an egg. And, he goes on and brings in a lot of the stuff about like tame and that sort of thing. So, there are a lot of like Levin-specific references and sub-references. So that's what that table is. I don't know if you had anything to say about the table itself. If we had any questions about that or any comments?
I just thought it was helpful to see a bunch of different examples from different disciplines, just of completely different phenomena that all follow this pattern. I thought the art line was interesting in light of what Jesse was talking about also.
Yeah, he has like two examples here: science in the short term and science in the long term.
Yeah.
So science in the short term are talks and manuscripts, and like we just said, his talks and manuscripts are connected here in like these. You have a reference, reference number. That's a manuscript that it gets. So you have a bunch of manuscripts in this network module. It gets connected to this other paper. It serves as the Bowtie hub, and then that can serve as to connect to another, module of talks and so forth. And so that's science in the short term. Science in the long term is ideas and paradigms and explanations. So it's like broader concepts, but they connect in the same way. Like we might have like a network of like a citation network, or we might have like a knowledge map or a frontier map, as Jesse likes to say. And then Jesse says epistems and other Foucault type stuff. What are epistems?
I meant to say epistemes.
But
epistemes. I think I said all right. I think, and correct me if you know better, Amanda, but basically, Foucault kind of sees it like episteme is sort of not quite like Kuhnian paradigm, but more a big macro zeitgeist by which everything is sort of just everything is sort of dominated by the view at the time, sort of like, in the Scholastic or Middle Ages era, everything like people until that was questioned, like you didn't question, like divine rule and God did this and that and the sun, the earth is the center of everything and so on and so forth. Like I guess it's called, as looking it up, an episteme is an epistemological field that establishes the conditions for knowledge. It's the guiding unconsciousness of subjectivity within a particular epoch. So, like he mentions three epistemes, like the Renaissance, the Classical era, and the Modern era. So it's a little bit different than like Kuhnian, stuff, but more like really big. I think one of his takes on it is basically you can't really. It's very like dominant underpinnings of stuff. So I don't know if anybody wants to add anything to that. But,
Yeah, really, I think it does speak to the whole like what is a unit of experience. Like, he talked about several hundred milliseconds, and that's kind of like the short-term memory analogy. But like in this case, it would be like an era, maybe hundreds of years. It could be like 20 years, depending on the field that you're talking about. Having that sort of frame of reference, and then everyone knows that that's how things are talked about, and then that changes over time.
Yeah, I think it'd be really fun to actually compare this, like from episteme, which is this huge, like very long term, like the idea of long term as in, well, it's sort of this mix between long term. If short term, something where like short term meaning conditions are not changing, it's sort of like this big mega short term where the conditions aren't changing, for the epistemological stuff or how it's done at the time, even though it is an era. I think that this is something I'm very particularly fascinated with, I would say, on many fronts. The last thing I'll say before we go is basically it'd be fun to play around with this idea and sort of this stigmergic, I don't know, I really don't want to use the word affordances, but like stigmergic um, validity or like the nature in which the stigmergic activity can take place. Like in the case of ants, they have that the pheromonal stuff, but it's not permanently there. It can change. It can change in a day or a couple seconds or like next month. Like there's different zones, and there's probably a specific time range, for how long it takes to change, and how long that ant community is doing something. But there's sort of a zone of relevance to that thing, and how maybe for an episteme, the stigmergic essence of what that is one thing, and different kinds of memory different and so on. So,
all right, that's a very good point. Yeah, we should look into that. Amanda,
I don't have anything to add.
okay.
But yeah, that was interesting.
All right, I guess that's it for today. I know Morgan came in like right at the end, but
do we want to have any other meetings before the end of the year? I know we're kind of close. We have sort of a couple weeks until the big final holiday times, but I know I've kind of put a hold on cognition futures, and that's probably a wise choice for me for now. But I'm willing to try to meet again one time, but we'll see. I'm otherwise in sort of finals period. But
where are we today? The 5th?
Today's the 5th.
So the next Cybernetics would be like the 19th. Does that too close to the holidays for people? Or?
Well, we could meet next week, I suppose, but I don't know if there's anything we want to meet about next week anyway. So
I'm flexible. We could pick something from that Von Forrester collection.
Yeah.
But there's also no rush. It can wait until after the holidays.
Yeah.
Okay, maybe we can look at that and come up with something in the Slack and decide later. Because I don't really know right now myself. But it's good to talk today.
Yeah, good to talk.
Yeah.
Yeah.
Right.
Talk to you soon.
Thanks. Talk to you soon. Take care. Okay, so in the first 15 minutes of the meeting, we went through those screenshots, which are sort of an overview of the discussion, and we identified a couple references and footnotes that are kind of interesting. So why don't I go through that list now? So this is the paper. This is in the journal Entropy. So this is it was published. And so Levin, talks about these bow ties here, first of all, and kind of going through some of that, what he kind of means by bow tie. So he talks about how there are these profound symmetries between the collective intelligence of neurons in navigating 3D spaces and that of non-neuronal cells navigating anatomical morphospace. So he's done a lot of stuff with electricity and electrical potentials in cells, and of course making the connection between what neurons are doing and non-neuronal cells are doing in these, with these outputs, with neurons navigating 3D spaces and non-neuronal cells kind of navigating anatomical morphospace that they're trying to form patterns in. Many algorithms, competencies, failure modes, and molecular mechanisms are shared between the self-assembly / repair of the body and the emergence / maintenance of the mind. So he's making this connection between kind of the self-assembly of non-neuronal cells and the maintenance of a mind by neural cells. He's making that analogy. This symmetry allows us to think about the relevance of memory remapping concepts beyond brain and behavior, and of sender-receiver models. And sender-receiver models are it's a model in communication where you have a sender that sends a model to the receiver. The receiver has to be able to receive the model. They have to be receptive to whatever the sender is sending. And the sender has to be, kind of know how to target the receiver. So a good kind of analogy for that is axon finding and development. You have a neuron that sends out an axon, and that axon follows chemical cues, maybe to another neuron that's out in what is not a nervous system yet. It's this space within an organism, with an embryo, or it could be in a culture dish, or in a organoid where you have this chemical gradient between the cells, and they send this axon on. The axon has to find its way to its target. So there are different ways to sort of conceptualize these sender-receiver models. We have this paper, The Meaning of Biological Signals. That's citation number 37. We have this paper, Evolution of Signaling Systems with Multiple Senders and Receivers, considering the evolution of those kind of signaling systems, which requires some memory, but also some natural selection and some way that those things can be encoded, say, in development. Deception is cooperation. So this is, again, kind of a game theoretic thing where the senders and receivers are cooperating, but also just trying to deceive each other. And then 80 is by Planner and Godfrey Smith, communication and representation understood as sender-receiver coordination. And this is from Mind and Language, so this is more of a cognitive science view. So he talks about bow ties everywhere and this sort of bow tie motif that we talked about in the meeting. And it's really this remapping process. So he talks about the importance of this process is that it squeezes down complex states into a compact generalized representation. So this is where we have like this module of the network, and it encodes something, and it needs to go through the single node that connects to two modules of the network. And to do that, it needs to go through this single node, so it needs to squeeze down all of this information about the complex state into some compact representation. So it actually talks about this generalized representation as being kind of like an autoencoder, something we'd use in AI. So an autoencoder is kind of, he gives an image here, figure 3, where he shows this bow tie architecture. So the bow tie architecture is this thing here. So you can see that, and I was talking about like kind of a complex network, but this is actually modeled on an autoencoder where you have input data here, and then you have this encoding phase where the information gets encoded from that network module, which is the input data. You have this latent space representation, which is this bottleneck or the single hub. That latent space represents everything in the input data, but does it in a way that's compressed. So you kind of compress out a lot of the details, and you have this representation that then you can sample from and get, this reconstructed data, and this is done through this decoding process. So then you have this network module below the hub, and it's taking samples from the latent space and reconstructing the input data as this reconstructed data. He talks about this in tadpoles. So in a tadpole, you have a tadpole will grow to an adult, and that adult will produce, or actually the eggs form in the tadpole, and then the adult lays the eggs. The eggs represent an encoding process, and of course we can do that with there's DNA involved in that. There's epigenetic memory involved in that, and so in the egg you have this encoding of the organism, and then that egg though serves as a bottleneck, which then is sort of like, if you can think of like an egg as a latent space of an organism, and then it unfolds as an offspring of this tadpole, which is the decoding process of this bottleneck. So this egg is the sort of the node, the hub of this network that represents the tadpole or the adult in one generation, and then it serves as a bottleneck or as this compact representation which then informs a tadpole or an adult of the next generation. So basically, Bowtie architectures feature a low-dimensional compressed medium at the center through which information must come. Okay, so that's that. Now, we talked about a couple references. I'll go down to the references. There are a lot of nice figures in here. There's figure 6. This actually talks about some of the things related to stigmergy, where we have the cell, the tissue, the organism, the swarm, and they map to these things, these other things where biological systems are adaptively incorporating foreign material at every level of organization. And then this shows the bow tie here, where you have a gene regulatory network, a bioelectric circuit, and a biomechanical network with this bow tie hub in the middle, which takes information from one of these network modules, maps it through this hub, and then maps it to this other network module below. Okay, so this is, let's see. Okay, so actually, let's go through the footnotes first. So the footnotes we're interested in are 49, 50, and 51. 49 is related to the first screenshot. And so this is Paul Pietsch suggests that memory phase codes can be encoded in the resonance between atoms within living tissues. James Shapiro points out that there is no line of demarcation between information on functional molecules and biology. So these are citations 219, which is this book, Evolution of You from the 21st Century. There's this book 4, which is by Pietsch, which is Shuffle Brain. And then 3, or I guess that's 43. It's okay. So 43 is Shuffle Brain, which is a book by Hough and Mifflin. All right, so that's 49. 50 is this note that unconventional memory media can include dynamical states rather than physical substrates, as discussed in this reference here, 220. This is Feroz and Izquierdo, a dynamical approach to the phenomenology of body memory. Past interactions can shape present capacities without neuroplasticity. It's in the Journal of Consciousness Studies, 221. Biswas et al., Learning and Transcriptional Network Models, Computational Discovery of Pathway-Level Memory and Effective Interventions. And 222, Biswas et al., Gene Regulatory Networks exhibit several kinds of memory, quantification of memory in biological and random transcriptional networks. And that was in iScience. And then 51 is this computational simulations in the field of artificial life. show the willingness of evolutionary processes to exploit all of the affordances of the environment. And that is from Bird and Lazell, The Evolved Ratio and Its Implication for Modeling the Evolution of Novel Sensors. And 229, Lehman et al. The Surprising Creativity of Digital Evolution. And that was in Artificial Life in 2020. So those are the footnotes. Let's go down to the references. So we're looking at actually the senome, or the sensory genome. Reference 19 is Miller et al. Why Death and Aging, While Memories Are Imperfect. So I think this is one reference for the senome. And then 227, which is down here. Miller, Maluska, Reber, A Revised Central Dogma for the 21st Century, All Biology is Cognitive Information Processing. Okay, so then references 217, which is Sam Gershman, The Molecular Memory Code and Synaptic Plasticity, a synthesis that was published in Biosystems in 2023. 218 is Fields and Levin, Scale-Free Biology, Integrating Evolutionary and Developmental Thinking. That's from Bioessays in 2020. 223 is Nakajima, Physical Reservoir Computing, an Introductory Perspective. So we talked about the reservoirs, and I think what he's talking about is more in the spirit of reservoir computing, which is where you have this random network, and you connect to that reservoir computer, and the reservoir computer self-organizes. So like a typical neural network has layers, it has full connectivity, and then you derive weights from that full connectivity to describe how that network is configured. In physical reservoir computing, or in reservoir computing, you have these reservoirs that are basically these random connections of nodes. They aren't layers, but they're just kind of like complex networks that are random. And then the activity then produces weights that are adaptive. And so it's a little bit different way to approach generating weights, but it's also a very exciting and new area of research. So this is from the Japanese Journal of Applied Physics in 2020. And then 226 is Nirala et al. Modeling non-genetic information dynamics in cells using reservoir computing. This is from iScience in 2024. So he's definitely referencing reservoir computing. 65 is Anil Seth, Being You, A New Science of Consciousness. 74 is Anil Seth again, Interoceptive Inference, Emotion in the Embodied Self. That's from Trends in Cognitive Science in 2013. 34 is Robbins, Stable Engrams and Neural Dynamics. That's in the Philosophy of Science Journal in 2020. And 35 is Robbins, The 21st Century Engram, Widely Interdisciplinary Reviews in Cognitive Science from 2023. So those are all the references that we have for this paper. I wanted to go through and see what they were. Thanks for watching.